In this video, we'll look at integrating factors, which is a technique we can use to solve first-order linear differential equations when it's not already written in product rule form. So finding a first-order equation like the last one that is written out where the left-hand side is exactly a product rule from the start is very rare. However, there's a way we can convert an equation that does not have this product rule form on the left side into one that does, using what's called an integrating factor. So the idea of this is the following. We start with our differential equation, which in standard form is y prime plus p of t y equals some function g of t on the right. And our goal is to multiply both sides of this by some function mu of t so that it turns into a product rule term on the left side. So we're going to multiply both sides by mu of t and then expand out this left-hand side. So we'll see mu of t times y prime plus mu of t times p of t times y equals g of t times mu of t. Now I want this left-hand side to be a product rule. The first term here kind of gives us what we want. This is mu of t times y prime, which means that to balance it out, I need the second term to be mu prime of t times y, the y I have. So that means that for this mu of t to work, I need to have mu prime of t equals mu of t times p of t. Or if I drop the of t part of mu, what I will see is that I have mu prime equals p of t times mu. But that's a separable equation. We can solve that. This becomes d mu over mu equals p of t dt. If I write mu prime as d mu dt, I can then integrate both sides, giving me natural log of mu equals what I'll write as capital P of t plus c, where capital P of t is the antiderivative of little p of t, and then I can solve for mu. So this function that I want here is mu of t is the exponential of capital P of t plus c, and it turns out the plus c here doesn't matter because I'm multiplying both sides by this same function, and so that plus c is e to the c is just a constant. So I can ignore that plus c and just get that what I want to multiply both sides by is e to the capital P of t, where this capital P is the antiderivative of p of t, which was the coefficient of y in the original equation. Let's see how this works out in an example. So we're going to solve the initial value problem, y prime plus 4y equals 1, with y of 0 equals 1. So in this, I can identify that my coefficient function p of t, which is the coefficient of y in the equation here, is 4. Therefore, its antiderivative, big P of t, is just 4t, because I'm integrating in t here, which then means my integrating factor, mu of t, should be e to the 4t. All right, let's try multiplying both sides by this and see what happens. If I do that, I will get e to the 4t times y prime plus 4e to the 4t times y equals 1 times e to the 4t. And if we look, this worked out exactly right in that this side here is e to the 4t times y prime. The product gives me exactly what I have above for that expression. And this equals e to the 4t, so I can now integrate both sides. And because this side here is a derivative, when I integrate both sides in t, what I end up with is e to the 4t times y equals whatever I get for the other side. In this case, if I integrate e to the 4t, I get 1/4 e to the 4t, and don't forget the plus c. And I can divide both sides by e to the 4t to get that my function y, the general solution, will be 1/4 plus c e to the minus 4t. But that's not what the problem wants. I'm supposed to have the initial value problem with y of 0 equals to 1. So then I can plug in 0 and see that y of 0 is going to be 1/4 plus c times 1. Since I want this to equal 1, this gives you that c should be 3/4. So the solution that I actually want is y of t is 1/4 plus 3/4 e to the minus 4t. That's how these problems work. They're all more or less of the same type, and they work out the same way for these problems. Now, because this process works every time for every equation of this form, there is sort of an explicit formula you can write for the solution no matter what the problem is. I would recommend against using this and just go through the same method every time, because that'll get you more into how it actually works. But there is a formula if you want to just see it, and most books will have that written there as well. So I recommend doing this process above every time, but there is an explicit formula. And this basically comes from the fact that we know that once you multiply by this mu of t, you're going to get a product rule on the left side. So we're always going to get the step where it's mu times y prime equals mu times g, where this is our g of t from the right-hand side. We can integrate this to get that mu of t times y of t equals the integral of mu of t g of t. And then I can divide both sides by mu of t to get the explicit answer. So you get that y of t is 1 over mu of t times the integral of mu of t g of t dt. And then if I want to solve initial value problems, I basically want to put the plus c into this part, so it's also divided by the mu of t, and then can solve for the c I need to solve that problem based on what I compute for this antiderivative here. So this formula is correct and works every time, but I would recommend going through the process because you'll see how it works more explicitly if you work it out via the actual method every time.